Good afternoon, madam. Can you hear me? Good afternoon, Priya Hassan, madam.
Hello. 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 No, I don't know.
You can speak something. Hello. Can you hear me?
Am I audible?
Yeah, I can hear you.
Is my screen coming on?
Not yet. You'll have to share your screen. Open the camera.
Is it coming now? Is it coming now? Okay,
So
is it
that
coming
we
now?
can. Yes.
Okay.
At the boundary, there will be a cold dense molecular cloud. And what happens is, if there is a pre-existing dense clouds, what will happen? At the boundary, a shock front will be generated, and which will compress the cloud, and eventually star formation will happen. And as a result, what again will happen is there can be possibility of existence of elongated type structures which are which point towards the massive sources. So here I have shown example of two such structures, like and which are, like you can see, they are like elongated in the
Hello. Can you hear me? Hello. Am I audible?
Dr. Uma, can you hear? Hello, is there somebody there?
No, good afternoon, sir. You're audible.
Okay.
Good afternoon, everyone. Good afternoon, everyone. I welcome you to this fifth day of 1 week online National FDP on fundamental mathematics. This program basically celebrates birth anniversary of Mariam Mirza Khani, the only woman field medalist till today. Now I call upon Jay Shri to introduce today's speaker, Mr. Hassan sir.
Thank you, ma'am. Good afternoon to one and all. I'm S. Jayashree, coordinator of statistics. It is my privilege to introduce today's speaker, Mr. Alap Hassan sir, on the fifth day of a 1 week of faculty development program. Sir has done 5 years integrated masters in mathematics. Sir is a research scholar at University of Hyderabad under the guidance of Professor M.S. Dutt. Sir is currently pursuing PG diploma in AI and ML, and he did summer project on algebraic topology in 2019 under the guidance of A.J. Jayanta in Goa University for 3 weeks. Sir completed project in masters on commutative algebra, building up to algebraic geometry under the guidance of Professor M.S. Dutt at University of Hyderabad. Sir has completed courses in the areas of analysis, measure theory, algebra, topology, and some name few. Sir not only interested in academics, but also his interests include boxing, football, painting, dance, etc. Now, I invite Alap Hassan sir to take over the session. Thank you.
Am I audible?
Sir, yes, sir.
Yeah. Are you able to see my screen?
No, sir, we can't able to see your screen. Now, right now we are able to see your screen.
Okay. All right. So since we're celebrating women's contributions to mathematics, today's mathematician whose work we study is Emmy Noether. So she was a very influential algebraist, and she was the daughter of also a very good mathematician, but she overshadowed him greatly. And named after her is a mathematical object called a Noetherian ring. And we will be studying these rings. So the ring is said to be Noetherian. So we hear all rings that we're working with are commutative rings. So R is our ring. And for today's lectures, all rings are commutative. Meaning A times B is same as B times A. And Noetherian rings are rings with ideals. Say we have a bunch of ideals I1 to IN inside our ring R, such that each is nested inside them, and we have a chain of these ideals. Then there exists a stage at which all the ideals past a certain point will be same as a given ideal. So this is called the ascending chain condition. And the language that is used associated to this is that we say the chain is stationary after a stage M. So this basically means that we cannot have an infinite chain of ideals going upwards. We may, however, have a chain that goes downwards, which can be infinitely descending. But when we are looking at containment, we will reach a point when we will reach a maximal element. So, examples of Noetherian rings. So, all fields are Noetherian rings, and that's because fields only have the trivial ideal and the whole field itself as a ring. These are the only two ideals of a ring, of a field. So this will have to have this property. And this is extremely crucial to algebraic geometry because there we work almost entirely with fields. And fields are Noetherian rings. Another important property, which comes more from the side of number theory, is of integers. So integers is a ring, and all the ideals of integers are of the form mz, where m may be any integer. So 2z, 5z, 3z, where mz are all the multiples of m. So over here, what happens is that given any number m, we have a prime decomposition for it. And using this prime decomposition, we can make a maximal chain of ideals, which will have mz on one end, mz on one end, and the biggest ideal would be z. So this is also a Noetherian ring. And this example is more crucial to algebraic number theory. So the way algebraic way Noetherian rings and all work is that we take the idea of integers. We take integers, we abstract out our properties, and we study rings. These are algebraic objects. So this is algebra, and this gets divided into two different flavors of algebra. One is a geometric version, and one is a number theoretic one. It usually works out is that we have various algebraic theorems over here, and we can interpret them either geometrically or number theoretically. And algebraic geometry is about studying the dictionary between the geometry and the rings of an associated space. Meanwhile, number theory has more to do with understanding a ring and its ideals and various properties of that. Their factorization, decomposition is much more important. So, when we're studying number theory, you're studying basically rings based off the integers. And integers have two important properties. One is what we're studying today, which is the Noetherian one, and the other is that of a ring itself. So, sorry, of prime decomposition. So, since school, we study something called the fundamental theorem of arithmetic, which is that given any integer m, there exists a unique prime decomposition of it. So m can be written as a product of various primes with specific powers, and this is of finite length. What we will be studying over here is a generalization of that to rings. So this will be a theorem called Lasker-Noether theorem, which is to do with the decomposition of ideals. Another important example of a Noetherian ring is if a ring is Noetherian, then the polynomial ring associated to it is also Noetherian. So, and hence the polynomial ring with two variables is also Noetherian, and inductively we get all finitely many variables for a polynomial ring of a Noetherian ring is also Noetherian. So, in the proof of this, we will see how most of these arguments are made. And it is always to do with this ascending chain condition. We only use that in our proof. And the most useful form of the ascending chain condition is to think of when n stabilizes. So this is an example of how a lot of these commutative algebra proofs are. And it's also an important proof. This was a result by Hilbert. It's known as the Hilbert basis theorem. So if you have a So what we are given is that ring R is Noetherian. We want to show Rx is Noetherian. The rest two will follow immediately. So if we have a chain of ideals in R, X, sorry, if you have an ideal I in Rx, I have to change color. We have an ideal I in Rx, then we can consider all the polynomials of various degrees, degree 1, degree 2, degree 3, and we, instead of studying an ideal in Rx, we will try to study a chain of ideals in R. Since R is Noetherian, we want a chain of ideals in our Noetherian ring. So we are trying to construct a chain. So what we do is we define In to be the leading coefficient of all polynomials of degree n inside I which is a polynomial in Rx. I hope that is clear. That is, I think, easier to read and understand. What is not difficult at all to see is that each of them is in fact an ideal. So for all those people who are studying algebra, I think they should try this as a small exercise. And we can also easily see that each of I is contained inside the bigger I subscript. Since we can always have a mononomial polynomial which comes from, say we have cmx from here, then we just multiply it by one more x and we get a polynomial cxm plus 1 which lives in m plus 1. So we have constructed a chain of ideals inside a Noetherian ring and we know that it will stabilize. So say it stabilizes at this stage in, we will set so yeah, so we can set this in as our choice of I, and we study the sets S0, S1, Sn, which are sets of polynomials of degree 0, degree 1, and so on, with leading coefficients from our I0, I1, and In. And then we just have to show that this generates the ideal I. This follows quite fast. So this is known as the Hilbert basis theorem. These proofs are something that a student has to go over some time, do it themselves. And for the purpose of this talk, it is very difficult to go over all the small details. But in algebra, it helps to do that. So what we're studying here is Noetherianness, and we can also have Noetherian in another context, which is what is a Noetherian topological space? And this is when it directly comes into algebraic geometry. So here we define, instead of ideals, we are looking at closed sets, and we look at chains of closed sets which satisfy the descending chain condition. So if you're given a set of closed sets C1, C2, C3, Cn, so on, and we have a chain of ideals that becomes smaller as we're going. Am I audible? Because I think something has said it stops sharing.
Yeah, we can hear you.
Okay.
The share screen has gone.
Coming now?
Yeah, it's fine.
Is the sharing of the screen coming?
Yes.
Yes, we can see your screen, sir.
Is the screen share visible?
Yes, sir. Just now we have seen your screen, but right now it's
Okay.
not.
Is it coming now?
Yes.
Okay. So this result is known as the Hilbert basis theorem. Uh, okay. We were at Noetherian topological spaces, and honestly, these Noetherian topological spaces come from when we reinterpret our algebraic result in geometry, we get these Noetherian topological space. So that is why over here we have a descending chain condition, which is the opposite of the ascending chain condition. So here, if we have a descending chain of closed sets, we will find them when we rearrange them in geometry.
I request all the participants to mute yourselves.
Hello, am I audible?
Yes, sir, you are audible.
Can you make me co-host so that I can share?
Sir, we have already made you co-host, sir. You can share the screen.
Okay, now I'm able to share. Um, it should start now. Is it coming?
Yes, sir, we can see your screen.
Okay. So in algebraic geometry, the shapes we study are solutions of equations. Like lines are solutions of equations. Circles, parabolas, so on. So you can have an equation, say x square plus y square is equal to 1. And this is a solution of when we graph this to get a circle. And we graph this in R2. Similarly, we may have something like xy, which is solution which is the x-axis and the y-axis. It's a double line. And xy can actually be written as x union x equal to 0 and y equals 0. So this shape, which is this double line, can be decomposed into this axis and this axis. Meanwhile, something like y is equal to x square, this is irreducible.
Hello.
Can you hear me?
Oh,
So what I'm trying to describe over here is that um, first thing, studying this equation is the same as studying this object. Studying this equation is the same as studying this object. And moreover, the way we can factorize this into x times y, we can break this into the x-axis and the y-axis. So when we look at all the solutions, let me write it down formally as well. Since in algebra, the forms are very bit. Okay. So that is Peter Poisson. So if we look at the set of, say we have a field K, A and K is the affine field of n dimensions over K. And this is basically isomorphic to K cross K cross K n times. So in our example, we were studying R2K, sorry, A2R, which is R cross R. And if we consider the topology generated by solutions of polynomials of Kx in K and K, we'll find that this will be a closed set topology. So these are, so if we consider all our solution of polynomials, like say every point will be a solution since x equals c or x minus c is always there in our kx. So we'll find points, we'll find lines, we'll find parabolas, all the usual algebraic shapes will come. And if we consider these as closed sets, we form a topology, which is that arbitrary intersections, finite unions, sorry, arbitrary unions, finite intersections are closed. And the empty set and the whole set is also in the set. So this is one important branch of algebra, which is algebraic geometry. The other is algebraic number theory. And an example of how that comes as a result of commutative algebra studied by Noether is the primary decomposition of ideals. So the way we have decomposition of any integer, say we have z, say we have any m belonging to z, we can find a bunch of primes p1 to pn, the prime factors of n, such that m is equal to m I no, pi alpha I, and this is unique. This is known as the fundamental theorem of arithmetic. So when we are studying general commutative rings, on adding the condition of Noetherianness, we are able to have a generalized version of this, which is called the primary decomposition theorem. So whatever properties integers show with factorization, which is will be mirrored in the form of ideals in our general Noetherian ring. So this result is actually a very was first done by Lasker, who was a student of Noether. But not this Noether, it was the father of this Noether named Max Noether. And Lasker had proved this in about 100 pages or so, making it one of the longest proofs in algebra at that time. And Noether managed to prove a more general version in closer to about 2 pages. So if we have time, then maybe we can go through this proof. So for this, I will mention something called Noetherian induction, which is basically the essence of all the what I was referring to earlier, that you have to construct a chain of ideals with a certain property. This is, and then that chain of ideals will stabilize. So this is how we prove most things in Noetherian rings. So it is a tool known as Noetherian induction. So let N be a Noetherian topological space. So I will give this example in terms of the topological space. This way it is easier to imagine something, and let P of X be a property of a closed subset of X. For any given Y which is closure in X, if, okay, so say we have our X over here, and we have a for any given y inside X, we find that all the subsets of y have a certain property P, then that implies that y in fact must have this property P. And that implies that X has this property P. So this is a small lemma of logic that has to be done individually. And this is the idea which will prove any given property for a whole set. And when we are studying things like rings, we already have certain structures of ideals. And we will look only at chains of those ideals. So this is an important notion to understand the proof of Lasker-Noether theorem. So it is a two-step proof. The first step is that every ideal is a finite intersection of irreducible ideals. And I will define what an irreducible ideal is. I haven't done that just yet. And step two is every irreducible ideal is finite intersection of primary ideals. So using these two steps, we get that every ideal I can be written as the intersection of finitely many primary ideals. These primary ideals are actually just generalizations. They're the right generalization of prime ideals, which is actually a generalization of prime numbers. So let's start with the proof. The first step is to show every ideal is finite intersection of irreducible ideals. And I haven't mentioned what an irreducible ideal is. So given an ideal I and R, if any ideals J and K which are not, okay, this is the better way to say it. So if you have any two ideals J and K, such that the intersection of J and K is I, then I must either be this whole one or it must be this whole one. So let's continue the proof of Lasker-Noether theorem. So if you have A, which is a set of ideals inside R, the set of ideals which are not finite intersections of irreducible ideals, then I cannot be expressed in this form. If it is, then that means either J is I or K is I. And so let's take a I which is not an A. So I can be written as an intersection of irreducible ideals. Say you have I written as J1 intersection K1. Then either J1 belongs to A or K1 belongs to A. We find that J1 belongs to A, then we set I1 as A. We find that K1 belongs to A, then we write I1 is equal to K1. So given an I, we have constructed a I1 which contains I. Using the same process, we can construct an I2 and a I3 until we have a IK. But since we are building a chain in a Noetherian ring, we must find that our IK must stop, and we will find a maximal K. So that if we have anything above K, if M is greater than K. But that means that we have written I as, oh no, then the problem is, there must be a problem because we cannot have a construction for a ascending chain and have it not be stationary. So we reach a contradiction and we find that A is in fact empty. So there is no ideal which cannot be written as a finite intersection of prime ideals. Then there's only a final step which is left, and this is in fact a slightly longer step, and it gets a little technical, but the technical part is just in some way just algebraic, and for study purpose you just have to understand that it works, not worry about where it comes from. A lot of proofs are similar, so it comes in some pattern as well. So we have the step 2 to show that every irreducible ideal is a finite intersection of primary ideals. So we have now shown that every ideal can be written as finite intersection of irreducible ideals. Now we want to show that this is further, every irreducible ideal can be written as a finite intersection of primary ideals. And since we can write every ideal I as a finite intersection of a finite intersection of things, it must be a finite intersection of things that gives us I. So step 2 is every irreducible ideal. Let's take an ideal I to be irreducible. Let A and B belong to I. Let's define JK to be the ideal generated by BK. So we find that as K will increase, this ideal will get bigger. And thus we find this chain. And let So since we have this chain of ideals, this stabilizes after certain states K. So let's K be that stage, and we have we set this wrong over here. JK equals, let's take it as dark J. And let's write J as, let's write K to be the ideal I plus the ideal generated by Bn. So we find in between, we find I is contained inside J intersection K. Now we were trying to find a C inside J intersection K, which is inside I, to show that both are in fact the same. So we have a C belonging to J intersection K, and we write I belonging to I, and we get Bn of C is also inside I. And when we multiply both sides by Bn, which is an element of R, so we can do that, and it will still fall inside the ideal, we'll get Cbn minus I is equal to Fb to power n. And uh, therefore we find Fb to power n is equal to Cbn minus I. This is inside I, and this is inside I. So we find Fb to power n also to be inside I. And that is equal to n. And that implies I is equal to J intersection K. So what we have shown right now is that every irreducible ideal is a finite intersection of primary ideals. So this is actually a very nice result because it captures the other property of integers, which is of factorization. And the importance of this work is that this work was originally done in over 100 pages, but Noether was able to do it a more general version in about 2 pages in very simple ideas that can be explained in over a period of a week or so. So this is what I wanted to show. This is fine. Any questions?
Participants, if you have any doubts, you can ask.
Okay, so I think there are no questions. I'll stop my share.
Thank you, sir, for readily accepting our invite in spite of your busy schedule. And please accept the certificate of appreciation, sir.
Thank you.
I just share the certificate to your mail, sir.
Thank you for giving me this certificate and this opportunity.
You're welcome, sir.
May I leave?
Okay, sir. Thank you, sir. Now we will start with the next session by Professor Ekta Agarwal, Madam, on improper integrals.
Am I visible?
Yes, Madam. Good afternoon, Madam.
Good afternoon. Am I audible? I hope I'm audible, right?
Yes, you are audible, Madam.
1 second. I will share my screen. There is time, right? We have 3 minutes, no?
Yes, sir. Yes, Madam.
Aya, कैमरा सेट कर दो. ये डबल स्क्रीन है क्या? All the participants are here.
Shall we start, Madam?
Yeah, 1 minute.
Okay.
Yeah, we can start. All the participants are here.
Yes, Madam. Now I call upon Manisha to introduce today's speaker, Professor Ekta Agarwal, Madam.
Good afternoon, everyone. I, CH Manisha, Faculty, Department of Mathematics and Statistics, RBVRR Women's College. Welcome you all once again to Day 5 of 1 Week National Faculty Development Program on Fundamentals of Mathematics, organized by the Department of Mathematics and Statistics, RBVRR Women's College. It is my privilege to introduce our speaker of today's session, Professor Ekta Agarwal ma'am, Associate Professor at Indian Institute of Management. Ma'am is working as a faculty in the area of operations management and quantitative techniques at IIM Indore. Ma'am holds PhD in maths from Tata Institute of Fundamentals Research and specializes in applied mathematics. The main aim of her PhD works was understanding of mathematical model and numerical methods for a hyperbolic system of balance laws. Ma'am was a postdoctoral research with Dr. Paula Gotin and Professor Ronaldo Colombo in the team of France. Her research deals with applications of hyperbolic partial differential equations to analysis of macroscopic models for pedestrian and traffic flows. Ma'am research interests are numerical approximation of partial differential equations, applications of non-local hyperbolic conservations, laws to crowd dynamic and supply chain management, and developing advanced machine learning model for interdisciplinary research problem. Now I invite Professor Ekta Agarwal ma'am to take over the session. Thank you.
Thank you for your nice introduction, and thank you team for giving me the opportunity to throw some light on improper individuals in this faculty development program. Any particular reason why everyone's camera is switched off? Or can I have people having the cameras on, or how does it work? Yes, Manisha, how does it work? Are they supposed to keep their cameras off due to some particular reason?
Madam, you can on the camera and share the screen and you can explain, madam.
Yeah, I know, but I'm asking for the participants.
Participants, madam, they have to off their cameras, madam.
They have to switch off their cameras?
Yes, yes, madam.
Okay, fine, no problem. Okay, I'm just asking this Bhargavi because it becomes important to communicate with the participants, and their cameras are off. I don't know whether they're listening or not. So I hope that they're participating and they will listen to me and answer my questions also if I have. Right?
Yes, madam.
Okay, no problem. Okay, so I hope that everyone is comfortable with something called as Riemann integrals. Everyone knows that what's a function, right? So function is a kind of relation between two sets where they follow some kind of rule that every pre-image cannot have two images and every pre-image should have an image and so on, right? So I hope everyone knows that what's the function, and related to that function there is another topic which is called integration. So I am assuming that everyone knows that what a Riemann integration is, and I'm going to deal with the next thing of the Riemann integration. Okay, so what is Riemann integration? You say that you have a function f which is continuous. I'm going to use the word CTS for continuous and bounded, right? So you are assuming that when I say continuous, the layman language, it does not have a break anywhere. You can draw it without lifting your pen in a closed interval. And bounded means that your function is lying between two ranges, right? So your function is always going to lie somewhere between this lower end and higher end. So you say that your function is bounded. So if your function is continuous and bounded on a closed interval AB, then you say that a function is Riemann integrable if you can calculate. So we define a term like integral a to b fx dx, and I'm not going to go into details of what this term means. When we say that you can calculate this integral, we say that this function is Riemann integrable, and for that the hypothesis for this thing to be defined is a priori, that you should know that your function is continuous and bounded on a closed interval. So whenever we talk about Riemann integration, it's always defined on closed interval. Okay, so how do we do it? What's the idea? That you know that you have learned how to calculate the area of a rectangle, you know how to calculate the area of a triangle and so on. And now given a random graph, when I say random graph, you don't know the shape of the graph, and you want to say that somehow I know that how to calculate areas of rectangular regions or triangular regions. Can I calculate the area of the region which is under this curve? So you want to extend your area concepts to a area under a general region. So you say, okay, I don't know how to do this, but what I can do is somehow if I can approximate this region by some rectangles or triangles, hopefully I will be able to calculate the area under this curve. So what do? You say that, okay, so if you have a function like this, you have an interval AB, and you want to know that what is the area under the curve. So you will say, okay, I know how to calculate the area under the rectangles. Maybe I can draw some rectangles. Okay, I can draw some rectangles like this. These rectangles are of your choice. I have drawn in some fashion. There are infinitely many choices of these rectangles possible. Similarly, I am dividing here my AB into 10 regions, right? You can divide into 100 regions, you can divide into 200 regions, you can divide into as many regions as you want. But if you see this picture, your area under this rectangle, area under this curve is more than what you require, because you are overestimating your all this red area more, and therefore you feel like that, okay, if I increase the number of the rectangles or increase the number of the subdivisions of the interval AB more and more and more, maybe I will be able to cover up more of I will be able to control this overestimation of the area, right? So that you feel you can check it while using tools like GeoGebra, or you can calculate it exactly whatever you want. But the idea is that you want to increase the number of the rectangles as much as you want. So when you say that you want to increase the number of rectangles as much as you want, it means that you can make this number as large as you want, right? So if Uma Maheshwari is going to take this number as 1 lakh, then Ashita is going to say, okay, I can make it as large as I want, so I am going to make it 2 lakh. That you can make it 3 lakh. So this perception in mathematics is called infinity, right? So we know that there is no large number, and if you can make a quantity as large as you want, then you say, okay, that quantity is going to infinity. So what do you want? Okay, so if my limit of this number of rectangles has n tends to infinity of the sum of these areas, so you are going to add this area plus this area plus this area plus this area, all the areas. So you are going to sum up all these areas. Let's call them A. So you add A1, A2, A3, A4, AK. If this limit, so you add them up and then you take the limit of this sum as n tends to infinity by, because you want to cover up as minutely as possible. You don't want to leave any region. You want to cover it as is at every instant. You want to cover it. You want to cover the region at every possible change. You want to capture every possible change. For that, you have to divide into as small rectangle as you want, or as many rectangles as you want. If you are able to cover this up, and if this limit exists, when I say this limit exists, this limit goes to a number s, for example, where s is finite and so on, then you will say that your f is Riemann integrable on closed interval A. Okay, so the Riemann integration is kind of extension of this area concept, which you compute on rectangles and triangles. You take a function on a closed interval AB, you divide it into many rectangles, and you let the number of the rectangles go to infinity. Then if as n tends to infinity, the sum of all the areas goes to a finite number, say s. If it is finite, then you say that your function is Riemann integrable on AB. And as obvious, this definition was given by a mathematician called Riemann, right? So what are the things which we require for this thing? You require a closed interval AB. You require a function which is continuous on closed interval AB, or at least, of course, you can do it for discriminant functions also, but your function should have a finite height. And we know that all continuous functions on closed interval AB always have finite heights. They're always bounded. Therefore, if you want to check about a function being Riemann integrable, you need to start with a closed interval AB and a function which has a finite height. These are the two hypotheses which you want. Okay, so now if someone may ask that why, from where did that integral sign come? Okay, so would someone like to guess that from where did that integral sign come? If this is my definition of something being Riemann integrable, so how will you motivate someone that why this integral sign is there? Someone would like to answer? Someone would like to guess? What's your gut feeling? Yes, someone? Yes, Mamta? Anyone? Anyone would, Harita, would you like to answer? Yes. Please, someone. See, I don't know about other people, but in my class, I expect my class to talk to me. If that is not the way it is conducted, then I will not ask questions. Bhargavi ma'am, am I supposed to ask questions or am I supposed to just lecture? Yes. Uma ma'am, Bhargavi ma'am, someone would like to tell?
Madam, you just ask the questions and then meanwhile in the middle you can ask the questions, madam, or at the last you can ask the questions, madam.
Okay, in the middle, no?
You can continue, madam.
Okay. Okay. So participants, I expect you to please talk when I ask you some question. If you don't understand something, please tell me. If you understand something, please tell me. If I ask you something, if you don't know, please tell me. Right? But at least I expect some answers from you. That would be very nice. Otherwise, I don't know in which direction a lecture is going. Okay. If you don't understand anything till now, please speak up. Okay. Yeah. Okay, fine. So F is Riemann integral. So from where did this definition come? It's very interesting. The sign, that is my feeling. Okay, it's my gut feeling. It's not there in any book. I feel that you look at the sign. This is the summation sign, right? And now what is happening in the summation sign? Your sum is becoming bigger and bigger and bigger. Why it's becoming bigger and bigger? Because your number of the rectangles are becoming larger and larger. So basically, you are stretching the sum, right? You are stretching the sum. So when you stretch this side, summation from top and below, you imagine you are stretching this sign, the sum sign. So this thing will go down, this thing will go up, and the middle portion will become flat, right? Become straight, vertically straight. So I feel, my feeling is that this sign has come from, the motivation might have come from the sigma, where you're stretching your sigma down and up, and therefore this becomes an integral sign. So where are you stretching? You're stretching all the way from 1 to n. So when your k equal to 1, you are in your first rectangle and you are very, very close to the point A. Therefore, the subscript becomes point A. And when your k equal to n, you are stretching to the n, right? So you are becoming very, very close to P. So this becomes integral A to B. Then this AK depends on the height of your function at a point in this first interval. So therefore, it becomes Fx. And your base of the rectangle, when you write this AK, imagine, right? This is a rectangle. So it will depend on Fxk into this space, which I call it as delta x, because delta x is the small length of the base of the rectangle. But when your n is becoming infinity, your del x is becoming smaller and smaller. And we have learned in differentiation that when our del x becomes smaller and smaller, we start denoting, this is a notation, we start denoting it by dx. Okay, so the way to learn or motivate the students is how this is coming, that when you write this summation sign, your fxk becomes fx, your del x becomes dx, your summation sign becomes your integral sign, your k equal to 1 becomes a, and your k equal to n becomes b. Some people, when we do these questions, they tend to multiply fx with dx. They will do all kind of jugglery. They will feel that this is multiplication and whatnot. Please note that this is a notation. It does not mean anything else. It says that if your function is such that this limit is finite, then you say that function is Riemann integrable and your s is equal to this. I don't want to keep writing s and s and s again and again. And I want the notation to be compatible with f and a and b. Therefore, I introduce this notation. Alone, this notation does not mean anything. This is just a notation. This is not a multiplication, nothing like that. Okay. So if your limit exists, you call those functions as Riemann integrable. This is related to area under the curve, because when you want to define the area under the curve, you say that, okay, I will check whether my function is Riemann integrable or not, and then I will calculate this integral using some techniques or using this limit. if I'm able to find an answer, I will say that the area under the curve is this thing. Okay, so now there's a whole bucket of various methods to calculate this integral, but the definition says calculate this limit. If this limit exists, this is the integral. So now it's in general. So suppose I give you sin x. That can you prove that sin x is Riemann integrable? So some people tend to do this. Okay, if I ask you something is Riemann integrable, they will say, yeah, it's Riemann integrable because I'm able to say that it is c minus cos b. No. This is a formula which someone has given you. This is a technique to calculate this, but to check that whether sin is Riemann integrable or not, you really need to calculate that limit, which is not possible in every scenario. For example, how many people feel that this guy e to the power minus x square dx is Riemann integrable? What do you think? It's Riemann integrable. Anyone would like to answer? Anyone has seen this e to the power minus x square or e to the power sin x? E to the power sin x. Do you think that it's Riemann integrable? Yes, someone would like to say something. You have seen it, not seen it? Yeah, someone. I don't want to cold call really. Someone is putting in the chat. Okay, I'm not audible. Somebody is saying I'm not audible. Yes, am I audible?
Yes, ma'am.
Yes, madam, you are audible.
Okay. Okay, Harita, so since you have answered me, can you tell me, have you seen this kind of thing? Yes, Harita. Lakshmi, have you seen this thing? I saw your mic on. Can you tell me, have you seen this thing ever? E to the power sin x. Okay. Okay. So, so e to the power sin x and e to the power minus x square. So when you try to do integration, you will see that whatever techniques you try, you cannot calculate the integral of e to the power sin x or e to the power minus x square directly by the standard methods, right? And if you try to calculate this thing by limit definition, which I told you, it's crazy. You cannot really calculate it. It's not possible. But still, these integrals, we cannot say that these are not Riemann integrable. Some people have misconception that these are not Riemann integrable because they cannot calculate it by direct methods. But there is a theorem which says that every continuous function in this world on closed interval AB is always Riemann integrable. There is a theorem. Okay. Since exponential is a continuous function, sin x is a continuous function, e to the power sin x is a continuous function, therefore this guy is Riemann integrable on closed interval AB. Yani, if I am able to if I want to calculate the area under the curve of this guy, it is a finite number. Or if I keep making the rectangle smaller and smaller and smaller and smaller, and I take the limit of the sum of the areas, it's going to be a finite number. So I can talk about this. Okay, I can talk about this. Similarly, e to the power minus x square, people who know statistics or probability would have seen that this particular function comes as a in your normal distribution. So you can calculate the probability of a random variable between the 2 points A and B, where the random variable is normally distributed using this integral. It's a very, very important integral which comes up in probability and statistics. Again, if you try to use normal methods of substitution or whatever for this function, you cannot do them. They cannot calculate them directly. But you cannot say that these are not Riemann integrable. This is Riemann integrable because it's a continuous function. So when I want to take the area under the curve of this guy, it's going to be finite. So it's similar. Okay. So, but our topic, so this was just a quick revision of Riemann integrability, but our topic is not Riemann integrability. Our topic is what happens if you have, so what are the two things which we decide that we are going to take a closed interval AB, and the second thing is that we are going to take a function which is bounded on closed interval AB. So these are the two things which we require if we want to calculate, if we want to define Riemann integrability. But what I can do? Suppose I want to calculate the integral of this function. and this function is like this, okay? So as it becomes, it never touches this line, x is equal to 0, but when it starts approaching x equal to 0, it blows up, right? It blows up. Similarly, I can go down and down and down, and I keep going on the x-axis. It never ends and it keeps going on, right? So I want to calculate the area under such curves also, okay? And your first impression may be that this guy is not, the area is not, okay, because the region is infinite. Similarly, I can have something like something like this, okay, again something like 1 by x square. So if x tends to infinity, 1 by x square goes to 0, and as x tends to 0, 1 by x square goes to infinity. Again, by your gut feeling, you might want to say, some of you might say that this region is infinite, so area has to be infinite. Some of you might say, no ma'am, look at here, when I am going closer to 0 or infinity, the region, the tail is becoming thinner and thinner and thinner, and since the tail is becoming thinner, it looks like that the area under this curve will be finite, right? You cannot really say by looking at the curve that whether it's going to be finite or not. The point is, if I want to talk about area under the curve, I have learned one concept. I started with rectangles and circles and triangles. Then I wanted to area under the curve, but there was a restriction that when I'm calculating the area under the curve, I have to have a continuous function, and it had to be a closure to limit. But now if I look at this function is not bounded because it's blowing up near 0. In fact, it's not defined at x equal to 0. Similarly, I'm not sitting on a closed interval because I'm able to define this function in an interval as large as I want. So it is not satisfying any of my hypotheses, right? Not defined on a closed interval AP, not defined on continuous function. So I'm in a fix. But whatever concepts I have learned, I want to extend. Okay. So how do we do this? Okay, so let's suppose I want to calculate this. Okay, so let's say this is some function f(x), where as x tends to infinity, function is becoming 0, and I'm starting with the point A, and I want to talk about this area. So I want to talk about something like a to infinity f(x) dx. I want to talk about this integral. Okay, and I'm taking this liberty to write a to infinity because I know that I am going to reading the area under the curve when your interval is becoming infinite in the positive region, right? So how will I do this, right? What is the natural way of doing it? Someone would like to think about it, say about it. What is the, given that we know Riemann integrals, what is the most natural way of extending this definition? Yes, Lakshmi, you want to say something? I see your mic being on. Soma, you want to say something? No one wants to say anything. You can put in chat if your mic is not working. I want someone to give me direction how this should go ahead. It's not that you should know it. It's that what your gut feeling is, that how will you calculate. Just some gut feeling I need from you. Something which you feel it should be there, like from a layman perspective. No? No one? You want to try? No, it's just that just try. I just want to see that what you feel about it. No one wants to try. Soma, you would like to try? Soma, your mic is still again on, but you are not speaking. See, I am used to a very interactive classroom. Okay, if you don't want to speak on mic, you can put in chat, but please speak up. If you're not understanding, I will slow down. If you're understanding very good, I will pace up. If you have to say something. Yes, there's someone called Jhansi Rani. Yeah, Jayashree. No one wants to speak. Looks like no one wants to speak up. Doesn't matter. Okay, fine. Yes, Jaya, I can see, hear you. Okay, so how do we do this? Okay, So one natural way of doing this is you know what do you need for your Riemann integrability. You need a continuous function and you need a closed interval, right? So what you are saying, okay, if I am sitting till B, for example, if I am Monica, you want to say something? Then put in chat if you have something to say. Your mic has an issue. Okay, so I can calculate up to B for some any point B I want, right? So I am able, I can calculate up to here, I can calculate up to here, I can calculate up to here, I can calculate up to any point where I stop. Why I can do that? Because between A to any new point, my function is continuous, it is defined on closed interval AB. So my integral A to, let's say, B fx dx is a finite number. Why it's a finite number? Because f is a continuous function on any blue interval A, right? And now, do I want to stop at B? No, I don't want to stop at B. I want to drag this blue corner more and more and more and more. I don't want to stop anywhere because I have been told that find the area till you don't stop. You just keep on going. So how do you do that? You integrate till B, any point B you want, and then what you want to do, you don't want to stop at B because you want to make it more large each time. Therefore, you put limit B tends to infinity, right? So this integral A to infinity fx dx is when I put a dot and a equal to, it says that it is defined to be like that. Okay, no, God did not tell me that it has to be like this. As a mathematician, someone took the motivation that I knew rectangle, from rectangle I want to bend to a curve. I restriction had to be in a continuous function and a closed interval. From there, I am extending to a curve which is continuous, but it's being integrated on an infinite interval. Therefore, how do you do this? You use your previous concept. You integrate up to B, till there you can do because you're sitting on a finite interval, and then start dragging B to infinity. If this limit exists, means this limit is a finite number, you say that integral A to infinity fx dx converges to that number. If this integral is infinity, you say that your integral diverges. If this integral is minus infinity, you say this integral again diverges. If this oscillates, this integral oscillates. Do you understand this? Yeah. So what is the idea? The idea is, if you know, you first check whether your function is continuous. If it is not continuous, anyway, whatever we are doing is out of question. First of all, it has to be continuous. If it is continuous and you are sitting on an infinite interval, you integrate till any point C and start pushing that point C to infinity. If the resulting number is a finite limit, your integral is going to converge. If it's not finite, then you diverge, right? And why are we talking about convergence and divergence? When you talk about, when you are sitting, have a limit sitting here, right? It's kind of a sequence, right? And we want to, when we talk about sequence, going to a finite number, we talk about the terminology is convergence. We say that convergence, right? Because it's a limit. It's fine. Any doubts here? Please ask. If you have any doubts, please put in the chat box. If you have anything, if you don't understand this. If you understand this, please give me a thumbs up, please. Thumbs up at least. Yeah, Bhargavi says very good. Bhargavi is saying where I understand. And who else? And Jhansi Rani, please can you change your name if it's not your real name? And if it's your real name, let it be. But if it's not, please go back to your original name. Yes. Anyone? Manisha says yes. Okay. Okay. Fine. So let's do one question. Okay. So let's do one question. 0 to infinity sin x dx. Okay. I want to integrate this function sin 0 to infinity sin x dx from 0 to infinity. Yes, Nikita, you want to say something? See a yellow box, not your name. So 0 to infinity sin x dx. Yes, is it a continuous function? How many people feel that sin x is a continuous function? Yes, thumbs up please. Whoever feel that it's a continuous function. Quick thumbs up if you feel that sin x looks like this. Sin x keeps on going. How many people feel that there is some problem with the continuity of this function? Okay. Okay. So no thumbs up means there is no problem, or no thumbs up means you don't know whether it's a continuous. Okay. So it's a continuous function. Sine is our favorite function since you were in class 9, 10. It's a nice snake kind of function. It goes up, comes down from -1 to 1. Okay. So sine x is a continuous function, and I want to integrate it from 0 to infinity. How do I do this? I will integrate it from some 0 to b, and then I will drag b to infinity. Okay. And when I do this, this becomes sin x ka integral is minus cos. So this becomes cos 0 minus cos. Okay. And now the question is that when b tends to infinity, cos 0 is 1, you get 1 minus cos b. And now you want to send b to infinity. Okay. So when I send b to infinity, then what happens to cos b? Yes. What happens to cos b? Anyone would like to say something? Archana, would you like to answer? Archana 07. Yes. If you would like to answer in your bandwidth issues, please put in chat your answer. Yes, Shirisha, you would like to answer? Okay. So what happens is when b tends to infinity, your cos b is an oscillating function. Goes up, comes down. Goes up, comes down. So it keeps on having the same pattern, as you go ahead. So when b tends to infinity, you don't know which number you're going. You know that cos pi is 0, cos pi is 1, and so on. But when b is tending to infinity, you know that b is a very, very, very large number. And if you select a large number, you can choose a larger number. B can be larger than that, right? So when you do so, you don't know where cos b will go. Because cos b changes shape. You don't know where it will go. Therefore, as b tends to cos b infinity, cos b can move to 0, cos b can move to 1, cos b can do anything it wants because you don't know where it's going to go. And therefore, this limit does not exist. Right? This limit does not exist. Why? Because your cos b as b tends to infinity does not know where to send cos b to. And therefore, this limit does not exist. And therefore, sin x is not integrable on 0 to infinity. But sin x is integrable on every finite interval. But it is not integrable on 0 to infinity. We call these integrals, such kind of integrals which are defined on infinite domains, we call them as improper integrals. Why we call them as improper integrals? Because they are not properly behaved integrals, right? Our properly behaved integrals were something which were defined on closed interval AB and which were defined on continuity where the function of continuous. But now we call them as Riemann integrable functions, and that is the definition which we love. But since here my guy is behaving in a crazy way, it's not sitting on closed interval, I'm not able to use my definition of proper integrals. Therefore, I give them a special name which is called improper integrals. And to define the improper integrals, you just define a proper integral up to a certain limit and start pushing the limit to infinity. That will give you the answer. Yeah? Okay. So let's do one more. Yes, this you have to do, like Bhargavi ji told me that I can ask you questions. So please try this. What is this? What is going to be this integral? Please try this. 1 to infinity 1 by x square dx. So what we have to do? Again, 1 by x square is a continuous function on this whole infinity. Why? Because it's not going to have a breakup. Right? As x tends to infinity, 1 by x square is equal to 0. It's going to be bounded. It's not going to go to any height which you don't want, and therefore it's a nice function on 1 to infinity. But the domain of the integration is infinite, and therefore I need the improperty. How do I check it? I know that it is domain is becoming infinite, but I have to integrate into a finite domain up to 1 by b x square dx. So maybe if the graph looks like this, I want to integrate from 1 to infinity. I integrate till b and start pushing. Right? And what is this? This is equal to limit b tends to infinity minus 1 by x from 1 to b, which is equal to limit b tends to infinity minus 1 by b. Okay. So when b tends to infinity, 1 by b goes to 0, therefore this goes to 1. So what I have got, that the region under the curve 1 by x square from 1 to infinity, though this region is infinite, the area under the curve of this infinite region is 1, right? So how can it be possible? Yeah. Someone would like to say that, to comment on this, that integral is infinite, keeps on going and going and going, but the area under the curve or the integration is a finite number. Why is this possible in this case? Yes. Monica, would you like to answer? Okay. So this is true because your the 1 by x square is becoming thinner and thinner and thinner as x is going to infinity, and therefore though the curve has an infinite region below it, but the input by that infinite region or the tail of that infinite region is minuscule. Why I am saying tail? Because I am looking at the behavior of this integration as b is tending to infinity. Yani I am looking at the behavior of the tail after b. What happens to the tail of this function as b tends to infinity? In some sense, it's saying that the tail is so thin that it's not contributing to the area. Do you understand this? Let's do one more. Okay. Or we can also do 1 by x. Okay. So what is this? Again, 1 by root x is not going up anywhere between 1 to infinity. It's a continuous function. And how do I calculate this? Again, I know that it's a continuous function, but it will be integrated on an infinite domain. Therefore, this is equal to limit b tends to infinity integral 1 to b 1, and this is equal to limit b tends to infinity. This is equal to root x into 2. Why? Because x minus half integral of x minus half dx is equal to x minus half x1 over minus half x1. This becomes 2 root x from evaluated by b. So this becomes b tends to 2 root b minus 2. Now when b tends to infinity, root b tends to infinity, therefore 2 root b tends to infinity. Put this comes. Therefore, your 1 by root x also looks like this only. If you see on GeoGebra discourse or anything, this looks like this only, but here the tail is thicker than 1 by x square. So 1 by x square lies something like this, and 1 by root x lies above. So the tail of 1 by x square was thin enough not to give additional area. but the tail of apex is thicker, so that it's contributing to the area and making it infinite, right? Both are infinite regions, but depending on the behavior of the function near the rear end, it's going to decide that whether subset is going to decide that the area under the curve is going to be finite. Yeah. Any doubts? Any doubts here? Yes. Someone would like to say something? Any comments? Are you understanding or are you not understanding something? Some feedback, please. Yes. No feedbacks. You're listening? Kita, you want to say something? Okay, how many people understood? Please raise your hands. How many people did not understand? Please raise your hands. Bhargavi, you are the coordinator. Bhargavi or Uma ma'am? Okay. So Bhargavi, the point, okay, actually I expect them to participate, because if I'm explaining something and if I'm asking something, do you understand or not understand, I expect them to at least raise their hands or de-raise their hands, right? Otherwise it's, I don't know. So I don't know if they're listening or not, right? That's the point. I want them to listen, I want them to absorb, and if they have anything understood, not understood, please explain again. Kuch to, some bit of participation is needed, but it looks like they don't want to participate. So minus infinity to infinity x dx, right? So now how do you calculate this? So we have not learned about this, right? Because now I have a completely infinite region, right? It's going, the region is going to head on the positive side, the region is going to head on the negative side. So I have something like a function, let's say like this, which is going on something like this, which is going on both the sides, right? And the function is continuous, right? But I don't know how to take care of this. So what I will do, I will say that I don't know my definition, that my definition cannot cover the complete range of figure line R, but I can break it at any point I want. So let's say any point C you take, you calculate this region, you calculate this region, and if both the areas are finite, both the integrals are finite, then you say this is equal to minus infinity to C fx dx plus C to infinity fx dx if both of them are finite. When I say where both of them are finite, it means that if one of the region has already become infinity, you don't even need to calculate the other region, because in the sense of improper integrals, you have already, there is nothing called minus infinity to infinity. You calculate from minus into C, or you calculate from C to infinity. If both the regions are finite, you say that the total integral is the sum. If any of the thing is infinite or oscillates or does not converge, then you say that your total integral is going to converge, because one part of the thing is already diverged. That okay? Now the question is, how will you calculate minus infinity to C? What will you do? Again, you will go up to some point B. You will calculate up to C, from C to B, and you will start pushing B to minus infinity. Right? You understand this? Right? Okay. So now let's try to do this. Okay. So minus infinity to infinity x dx. Let's say this is equal to I break it at the point 0 and I say that this is equal to 0 minus infinity to 0 plus 0 to infinity if both of them converge. When I say both of them converge, this has to converge and this has to converge. So what happens to 0 to infinity x dx? 0 to infinity x dx is equal to limit b tends to infinity integral 0 to b x dx, right? Which is equal to what? B square by 2 and b tends to infinity, b square by 2 goes to infinity. Therefore, this becomes infinity. Since one part has already diverged, there is no need to calculate the complete part because your one part has already diverged, right? So let's look at the graph of this. Okay, so the graph is something like this, right? Now, if you remember your finite integrals or in a layman sense, right? What are you going to say? Okay, you will say, okay, ma'am, look here. If I move b distance on both the sides, then this area is going to cancel with this area because these are two same rectangles upside down of each other. So this plus this is 0, therefore this plus this is 0, therefore this plus this is 0, this plus this is 0. Therefore the whole area under this right hand side should cancel the whole area under the left hand side, right? Yes. So you may say, okay, calculate the area from minus b to b x dx and set b to infinity, right? And since you may say this is an odd function, the integral in odd function is 0, or you can see historically that minus b to b x dx is going to be 0. So you will say that limit is 0, therefore the answer is 0, right? Which we clearly know it's not right because how it is defined, like how it is defined. I calculate on the right region, I calculate on the left region, check if both of them are finite, any one of them is infinite, I say it is diverging. But what is the catch? Okay, the catch is how when you are calculating from 0 to infinity, you want to drag this guy b to infinity. Similarly, you want to drag this guy to minus infinity. Now you imagine you are two friends, okay? You are starting from center point and you have decided that we are going to reach, important, I'm going to reach the two ends of the earth and we are going to travel infinitely in opposite directions. And you will say, okay, still I am going to travel symmetrically because we are traveling in the straight line and therefore the total the y distance should be equal to your distance. But what is the problem? The problem is that both of the guys are allowed to go to infinity. So this may so happen that the guy on the right is traveling at a faster speed at a faster speed than the left hand guy. Similarly, the left hand guy may travel at a faster speed than the right hand guy. They can travel at equal speeds also. They can travel at whatever speeds you want. You want them to go to infinity, but no one told that at what speed it's going to be. Because when I say b is tending to infinity, you say that b has to be larger than any number you want. Then how do you know that the large number which you chose and your friend chose are same? They can be different also, right? Since they can be different, when you are dragging this b to infinity and another number b to minus infinity, you don't know whether these two b's are equal. Since you don't know whether these two b's are equal, you don't know whether the point where you are stopping is symmetrical or not. Here you can stop it here also and set b to infinity, and here you can stop at a lesser point. Since these two triangles are not symmetrical, you are not going to cancel the areas. You cannot cancel the areas, and since you cannot cancel the areas, it is random. You may cancel, you may not cancel. It depends how far you go, and you are allowed to go as far as you want, and therefore, though in proper integrals, when you take an odd function, the integral of x is 0, but in the improper integral, though your region looks kind of symmetric from minus infinity to infinity, but infinity means you can make it as large as you want, and no one told that the largeness on both the sides is symmetrical. Since we don't know that the largeness on both the sides is symmetrical, we don't know that these areas will cancel, and therefore minus infinity to infinity x dx diverges, but minus 1 to 1 x dx goes to 0. Right? So this is the feature where improper integrals is different than proper integrals. Right? In improper integrals, you cannot assume anything which you know from proper integral except for the fact that continuous functions are relevant. Except that you cannot assume anything. This is one cliched example where minus infinity to infinity x dx does not converge, though it's an odd function. It's not going to converge because odd function definition is on a finite symmetric interval. And when you are sending me to infinity, you are told that you are sitting on a symmetric interval. Is that clear? And therefore, minus infinity to infinity x dx is not defined. It's infinite. It does not converge. Is that clear? Yeah? Any doubts? Anything you would not understand? Yeah? Okay. Okay. So let's look at minus infinity to infinity 2x upon x square plus 1. Okay. So again, it's an odd function because when you replace x by minus x, then you get that f of minus x is minus of fx. In some sense, you are again integrating on a symmetric interval, symmetric infinite interval, and your gut feeling is that it will be 0, right? But let's see that whether it's 0 or not. How will you do it? This is equal to minus infinity to 0 plus 0 to infinity. If both converge, right? So 0 to infinity 2x upon x square plus 1 dx is equal to what? It's equal to limit b tends to infinity 0 to b 2x upon x square plus dx. Like our usual definition, you take it to b and start pushing b towards infinity. This becomes what? How do you do this? You put x square plus 1 is equal to t. This becomes 2x, dx becomes dt. So this is equal to, so when x is equal to 0, so you are putting x square plus 1 is equal to b. So when x is equal to 0, you have b here, and when x equal to b, you have, sorry, you are putting x square plus 1 is equal to b, sorry. So you have b square equal to 1, and limit b is tending to infinity, right? So this is 1, and this becomes dt upon t, right? So again, your 1 by t is an odd function on 1 by t is an odd function, right? I can calculate this thing. This is equal to limit b tends to infinity ln of b square plus 1 minus ln 1. Ln 1 is 0. As b tends to infinity, ln of b square plus 1 is infinity, and therefore you, since your one part is going to converge, this total integral is going to converge. Although your 2x upon x square plus 1 is an odd function, but still the improper integral does not converge because one part is going to damage. Is that clear? Okay, now someone might say this thing, okay? They may say that this part is infinity and the left part is minus infinity. So when I'm doing, I will get infinity minus infinity. I will take infinity, maybe something like so also, and say that it's infinity to 0, so it's 0. Or you may say infinity minus infinity is 0, right? Please note that infinity is a perception. Infinity is not a number. So it says that when I say that infinity minus infinity, what does this mean? Yeah. To ask. Okay, so it's something like limit b tends to infinity b minus limit b tends to infinity b. Do you think it can be 0? Please note that it's not 0. Okay, you may think that these are the same terms and subtracting the same terms, therefore it has to be 0. But no, it is 0 if both the limits are fine. Okay, so this says, what does this mean? This means that when I say limit tends to b, b tends to infinity, b can be made as large as I want. Okay, let's take this as number g. Then you say again minus another number which can be made as large as you want. Okay, so I say g2. Now if g1 is equal to g2, of course this limit is 0. But who told that g1 is equal to g2? Because g1 and g2 can be infinitely made, right? Therefore, though to naked eyes, though to a layman will look like limit of b minus limit of b 0 because they're same numbers, but the whole problem is that they are not numbers, right? So you cannot apply your high school algebra to this, because when you're saying limit, you are talking about a perception. You have to see that if that perception is going to give you a finite result, of course you can subtract. But this says A is a large number, B is a large number, large minus large is what? You don't know. Depends on how large you want to go, right? But if you take limit of B minus B, look at the difference, please. Okay. First I am subtracting, then I am taking the limit, so the answer is 0. So this answer is 0 because B is a finite number, B is a finite number. I am doing B minus B, which is going to give me 0, and limit of 0 is 0. But in the first case, first I am taking the limit and then I am subtracting. Therefore, I don't know how large they are. Similar problem is happening in improper integral. First, you are calculating 0 to infinity, then you are calculating minus infinity to 0, then you are adding up, you don't know whether how they. Is that okay? Yeah. Okay, so I think this should do the job. I feel so. If you have understood everything, please, it's good. If you want me to ask something, if you have understood everything, then I can give you one question. Or if you want to ask me something, please do that. No? Okay. So, Bhargavi, I think we can close now. We still have time. Yes. Bhargavi, I think we can close. Who is the host?
Thank you, madam, for accepting our invite in spite of your busy schedule. And you have explained step by step clearly the concepts, all the concepts, as we are very much understood by your all the concepts, madam.
So I think we can close it here, or I have time. I can have more material if you want me to cover. We can close it.
No, we can close it, madam, as
Fine.
we have the validatory function also. Now I call upon Manisha to propose formal vote of thanks.
It is my pleasure to propose vote of thanks on behalf of Department of Mathematics and Statistics, RBVRR Women's College. First of all, I thank you today's resource person, Dr. Ekta Agarwal ma'am, for accepting our invitation in spite of your busy schedule. I thank to our Honorable Secretary, Hyderabad Mahila Vidya Sangam, Professor K. Mutyam Reddy sir, our Secretary cum Correspondent, Professor G. Sudarshan Reddy sir, and our Principal, Dr. J. Achyuta Devi ma'am, for their continuous encouragement and support in organizing such programs. A special thanks to Shweta ma'am for organizing 1 week National Faculty Development Program. I also extended my thanks to ICT committee for their continuous support for the smooth conduct of the program. A sincere thanks to all the participants who have attended and make it a grand success. Thank you one and all.
Thank you, madam. Please accept the certificate of appreciation, madam.
Thank you. Okay, so I can leave the meeting, ma'am.
Okay, thank you, madam. Now I call upon Dr. P. Uma, madam, to propose the vote report, FDP of the report.
Am I audible?
Yes, madam, you are audible.
It is actually a pleasant duty and also a tough duty to give a report of FDP, because pleasant because we learned so many things from the speakers, their lectures and so on, and tough because whatever they have said I cannot communicate the intrinsic values and so on. I just try. Professor B. Suri first introduced high school math problem of a mantis catching a fruit fly in a very simple way, and then led us to gently into the deeper topics like of number theory, like modular groups. He also talked about the generators of modular group and so on. Some of the very interesting identities were introduced. He connected the topics with the work of Mariam Mirza Khani, on whose birth initiative we are celebrating this FDP. Professor S.D. Adhikari talked about very interesting combinatorial number theoretic problems, chromatic numbers and how they occur, starting with the coloring of numbers by Scher and van der Waerden, and reaching to up to current problems. Professor Geeta Venkatraman talked about some of the famous women mathematicians like Emmy Noether, Parimala Raman, Sujata Ramdarai, Neena Gupta, and all. Geeta Venkatraman herself is a famous mathematician. How it's important to pursue mathematics if you are interested in it, in spite of obstacles, is the heart of the topic. As this FDP is celebrating Mariam Mirza Khani's birth anniversary, focus on women mathematicians is more. Next, she brought out good topics in good group theory. One of the open problems being how many non-isomorphic groups are there of a given order. She mentioned how one can connect groups with graphs and so on. This is a theme pursued by Pratima Panigrahi in the next day. Actually, while starting the FDP, we didn't have strict line of plan. We meant fundamental mathematics and so on, but as the speakers chose their topics, a nice pattern set in. Professor T. Kumar spoke about mathematical modeling in population dynamics. He started at the very beginning of known records of data collection, then brought up to date the modern data collection. He also spoke about Malthusian formula and brought it up to the latest formulation of PDEs of population dynamics. At no point the speakers thought one should compartmentalize and speak about only one topic alone. In fact, they encouraged students and faculty as well to unify their view in learning mathematics. It should not be strictly algebra, strictly analysis, and so on. You should combine your understanding and then proceed. As higher mathematics will demand something of everything. Dr. Nikita Agarwal gave us a brief introduction to Mariam Mirza Khani's childhood, which was very turbulent because of Iran-Iraq war and so on, and how she could overcome the obstacles to pursue a career in mathematics. She talked about Mariam Mirza Khani's work. Actually, it's a nice sliding from her childhood, how she overcame and then became a mathematician. Her work about two tori and simple closed geodesics on them. Simple closed geodesics have polynomial growth as opposed to exponential growth for the totality of closed geodesics. She also talked about polynomial mirror rooms and illumination by a single candle, and how only finitely many points are left out without illumination. Professor Pratima Panigrahi introduced graphs. He connected graphs with types of matrices and their role in solving graph theoretic problems. Calligraphs of groups and other algebraic structures were introduced. For example, connected zero divisor graphs with rings, and the graph is connected if and only if the product is zero. Like zero divisors are non-zero elements whose product will be given zero, which is a current area of research. These zero divisor graphs with rings. Professor Rukmini De's lecture is titled Minimal Surfaces and Maximal Surfaces and Some Common Properties. She spoke about how a harmonic function gives rise to a minimal surface. Showed a beautiful result that a combination of harmonic function and its harmonic conjugate, giving an analytic function, again gives a minimal surface. She showed all these things pictorially. Helicoid and catenoid, going on to other famous surfaces like Enneper's surface, Riemann's surface, with all interesting diagrams were discussed. Riemann's staircase. Professor S.N. Hassan spoke about two-body problem, three-body problem and their solutions. How an n-body problem with n greater than 3 cannot have a closed solution. He also spoke about orbital mechanics and Lagrange points for orbits and so on. He also spoke about famous women in the field of orbital mechanics and space launches, some Indian, some American, and so on. About Lagrange points, the orbitals are the orbits. It actually has an infinite family of orbits, so there is no clash of some artificial satellite hitting the other and so on. That's and today Alap Hassan spoke about Emmy Noether's theorem. Noether being the greatest woman mathematician again, he mentioned her work as Noetherian rings being famously named after her. Ascending chain of ideals, if they are stationary in a ring, we call them Noetherian ring. Actually, this being equivalent to having every ideal having finitely generated, every ideal being finitely generated is the point of interest. Also, if R is Noetherian, Rx is Noetherian, and every finite polynomial ring is Noetherian. Finitely many variables, that's what I meant. So he also said how a proof of 100 pages could be reduced to 2 pages with her ideas. Last but not the least, Madam Agarwal, Ekta Agarwal spoke about improper integrals, which are very difficult to understand. She put it nicely, all the famous ideals, famous ideas in trying to get infinite integrals by taking them as limits. How you cannot integrate some functions and how you can integrate some other things depending on the nature of the function. She patiently wrote down every idea, every example, and then made it clear how the function's nature is appearing in the result. So that is the report of the FDP. And we have had in these days of saying why maths and why you don't connect with other subjects and so on. We have had a very nice ideas flowing in from the very eminent speakers, and it's our great pleasure to have had this FDP. I thank everyone who cooperated in this FDP. Thank you.
Thank you, madam. I thank each and everyone for making this National FDP a grand success. Again, we will be conducting International E-Symposium from 23rd May to 28th May 2022 online. And we will be sending you the brochure shortly so that you can join this International E-Symposium. And again, we will be listening to the eminent speakers so that we can gain the knowledge. Thank you each and everyone. Now I'm closing this National FDP. Thank you.
एक मिनट लाओ तो वो एक तुमने आपको मोबाइल तुम्हारो एक वीडियो છે 9મી તારીખે છે ને મોટું હે એ શું કર રાજુભાઈ શું કીધું લાગે તો છે હાથી ઘોડા જેવો ફેર છે આમ હાથી ઘોડા જેવો ફેર છે હા